So hello everyone, this is lecture 5, and in this lecture we're going to talk about several decompaction techniques. The first learning objective is to understand the mechanisms and procedures of vibral compaction and vibral replacement technique. So we're going to talk about this new technique, vibral compaction, and the vibral replacement techniques. And the second objective is to identify the applicability and limitation of vibration type compaction technique. And the last objective is to describe the design guidelines for compaction using explosives. So in this stage, we're going to talk about the blast-induced compaction techniques using some dynamite and explosives. So there are several types of the decompaction techniques. So one of them is the pre-consolidation. So this is normally used for the fine-grained soil. And to speed up the pre-consolidation rate, people also can install some vertical drains and stone columns or sand columns and paper wick. And pre-compression is a class, or is classified as a hydraulic modification. So we're going to talk about this technique in details in the part in the hydraulic modification. And also, deep compaction can be achieved using some explosion, using some dynamite and explosives, and also the heavy tamping. So in the last class, we talked about the deep dynamic compaction using heavy tamping. And also the vibration can be used to compact the coarse-grained soil. So vibral compaction and the vibral replacement is one of these mechanisms. And the last one is, popularly people use the compaction grouting, and this is by injecting some zero slump mortar into the ground. We can compact the surrounding soils. This is regarded as a physical chemical modification, so we're going to talk about it in details in the later chapters. So let's move on to the handout. This describes the more details about the vibral compaction and vibral replacement. So vibral compaction is the arranging of particles into a denser configuration by the use of powerful depth vibrator. And this vibrator is also called as probe or vibral float. And the vibral replacement is the same. It has the same mechanism with the vibral compaction, except that the granular material is added and compacted during the withdrawal of the probe. So basically, in the vibral compaction, it used the in situ soil to fill the gap or fill the craters. But in the vibral replacement, you replace the in situ soil with granular material like gravels or stones or cobbles. So it results the stone columns as you withdraw the probes built with the coarse material that replace the natural ground. So while this vibral compaction is applied to coarse-grained soil, and vibral replacement is typically used to fine-grained soil. And objectives of these two methods are to increase bearing capacity and reduce the foundation size, and reduce the foundation sediment, and mitigate liquefaction potential, and permit the construction on granular fill. So pretty much the same with the deep dynamic compaction. And if you look at the class note, yes, here it shows the difference between the vibral compaction and vibral replacement. And you can see that in this vibral compaction, so you lower this vibrator, and as you withdraw, this in situ soil can be dumped, and it will fill the gaps, and it's more densely compacted, including the surrounding area. But in the fiber replacement, it's a cohesive soil or the fine-grained soil, and as you withdraw this vibrator or the vibrator, gravel pack or the sand pack or the stone column is built. So that in the end, you will have a stone column at the location that you inserted this vibrator. Okay, so then what will be the process? So this shows the process of this fiber replacement and the fiber compaction. So first is that you push this vibrator or the probe using some water jetting. So as you just spray or the jet out the water, and it will liquefy the soil so that you can insert the probe easily. Then apply the vibration to the surrounding soil so that it will compact the soil and it will densify the density. Then as you withdraw, and the soil will fill the gap so that when you take out all the probe, then you have a soil column more densely compacted. And here you can see that during this compaction, either imported or in situ material is introduced. So if the imported material is introduced, then it's called the vibro replacement, like the gravels or the stone columns. If in situ material is used, and typically it's called the vibro compaction. So the entire compaction process in the field can be divided into 4 stages. And stage 1, the jet at the bottom of the fiber float. And the water jet creates the quick condition into soil. This allows the vibrating unit to sink into the ground. And granular material is poured from the top, and the water from the lower jet is transferred to the jet located at the top of the vibrating unit. And this water carries the granular material down the hole. So the hole is filled up with the granular material. And the vibrating unit is gradually raised in about 1 feet lift and held vibrating for about 30 seconds at each lift. And this process compacts the soil to the desired unit rate. So typically the vibrating unit is a long rod shape. And so this has the vibrator. Vibrating unit. And the length is typically 3 to 5 meter long. And the weight, the mass of this vibrating unit is about 2 tons typically. And the vibration amplitude is less than 25 millimeter, but the typical value is about 4 to 6 millimeter. And frequency is about 40 to 50 hertz. And sinking rate and the visual rate is 0.3 meters, or about 1 inch. 1 foot per minute. And the water pressure and depth, it can be used to 3 to 15 meter and up to 30 meter. And improvement up to the relative density is 70 to 85%. Total depth coverage per day is about 200 to 500 meter. And the vibrating unit is typically electrically actuated or the hydraulically actuated. So you can find the electric type and the hydraulic type. And applicable soils are pretty similar to DDC, the dynamic compaction. The best is a sandy soil. And as the fine fraction becomes more significant, the effectiveness decreases. So you can see that zone 1 is here, so that in the sandy soil, this vibral compaction is very effective. And as you go toward the this side, zone 2, the effectiveness decreases. So in zone 2, too many fines, difficult to compact. Could use weak drains to increase the drainage, but the silt content up to 18%, clay content less than 3% is typically used for the zone 2. So there's a marginal the soil type that this vibral compaction can be used. And when the particle size is too large in zone 3, like a gravel soil, because it's difficult to penetrate the this vibrating unit or the probe, so it's very difficult to use it to gravelly soil. And especially in the zone 2, if the fine fraction is larger than 20%, then it's not very effective. So this can be also found in this graph. You can see that the blow count, this is the SPTN value, and SPTN value is about this as the fine fraction increases. So as fine fraction increases, the N value also decreases. So that means the strength of the soil decreases. But after the dynamic compaction, or this is a vibral compaction, right? It increases to here, right? Increases to here, but as the fine fraction approaches to 20%, the amount of the improvement is not distinctively large. Yeah? So it's not much improvement. Is achieved when the fine fraction is high. So this also shows the range of soil suitable for improvement by vibral flotation. And as the particle size increases, you can see that the A here, this is excellent for densification, but however, if gravel content exceeds more than 20%, then depth may be limited to 10 meter. And zone B, the sandy, where the sandy fraction is high, is the best. And in zone C, where you may have some fine fraction, then this fine fraction may hinder the densification. So it's better to use the vibral replacement so that you replace the fine grained soil with the coarse soil. So the effectiveness, overall effectiveness of vibral compaction technique can be tabulated like this, so that the sand is excellent and silty sand is a marginal to good, silt is a poor effectiveness, and clay is not applicable, and mine sport maybe it's good, and dumped fill, garbage, it will be dependent on the nature of the fill. And typically when the original N value, SPTN value of the soil is about 5 to 10 before you apply the vibral compaction. And vibral compaction design steps. So here, no stone column. So because it's a vibral compaction, it uses the in-situ soil, so no stone column is built after the compaction. So the typical design steps are pretty similar to the other soil improvement technique. So perform site investigation and compaction requirement. So here you determine the relative density or relative compaction, right? TR. Then develop the appropriate fiber compaction approach and establish the quality control criteria. So in this stage, you inspect the site after the compaction, whether the site is well compacted or poorly compacted. So the main design parameter is the spacing, here, the S. And vibral compaction over large areas is done in a grid pattern. So it's similar to the deep dynamic compaction. And grids can be of square or triangular pattern, square or the triangular pattern. And spacing center to center, spacing is defined as the center to center distance in the zone. So here you can see that from here to here is the spacing. And in the square pattern, from here to here will be the S. Spacing. So if the desire, if it is the desire to increase the density of the soil with the void rate in terms of the void ratio, so let's say that the initial void ratio is E naught, and you want to decrease this void ratio to E, then spacing can be determined by using this equation. So in the square pattern, S will be a function of E naught and the E times D. And in here, the D is the sand pile diameter. And in the triangle pattern, it's the same equation, but you multiply the 1.08 as a coefficient, which reflects the geometry patterns. So, yep. Then depths of improvement are determined from the site investigation. So this will be determined from the site investigation, and it tells you that how thick of the soil layer should be compacted. Then the backfill selection. So the gradation of both in situ soil and the backfill soil will influence the level of the improvement that may be obtained. So depending on the case, this in situ soil can be used as a backfill material, or you can use the different coarse material as a backfill material. Okay? Coarse sand gives a greater densification than sand, fine sand, evidently because the coarser material is better able to transmit the vibration. So the Brown in 1977 defined the suitability number as N for vibral flotation backfill. And this Sn is defined as this equation. And here the D50 or D20 and D10 is defined as the millimeter. So it has the unit of the millimeter. And Sn is, it doesn't have the dimension, so you have to be careful when you put the number here. So D50 and D20 and D10, it gives you the Sn, and as the Sn is small, it has better suitability. So 0 to 10 is excellent, the gravel or the sandy soil, and larger than 50, it's the material, the backfill material is not suitable for this vibral compaction. And the lower Sn value, the faster the viral float can be withdrawn while still achieving the accessible compaction. Because the speed of the withdrawal is related to the permeability. So as you apply the vibration, so it's going to increase the pore pressure, and then it will densify the soil. So then it depending on it. So if you take out this proof too fast, then it doesn't consolidate or compact the soil efficiently. So you have to wait until it densifies sufficiently, and then you move up to the next lift. So here are the important references for the vibral compaction. So we talked about the vibral compaction and vibral replacement in the handout. And if you look at the applicability, vibral compaction is best for the sandy soil, and as the fine fraction increases, the effectiveness of this vibral compaction decreases. But the vibral replacement, it's excellent. It has excellent applicability for silty sand here, because it replaced the in-situ soil with the gravel pad or sand column, a stone column. And the silt and clay also has some good applicability. The mine spoil has excellent effectiveness, and dung fill also has a good applicability. But the important thing is that to use this method, the vibrated hole must be able to stand up alone as you withdraw the probe. So soil must exhibit undrained shear strength of 40 to 60 kilopascal to stand alone in this bare hole with a relatively lower groundwater table. So this is one condition to satisfy this vibral replacement applicability. And this is a very interesting graph showing the vibration level of each method. Here it compares the vibral compaction versus the vibral dynamic compaction. And when you look at the peak particle velocity, dynamic compaction has much larger particle velocity, and vibral compaction is in this range here. So you can get the feeling that the vibral compaction has low amplitude but has many repetitions, so they vibrate and densify the soil around this vibral the compacted hole. And the relative density achieved by this vibral compaction is about 70 to 85%. So commonly it's considered as technique that can achieve the up to 85% in relative density using this vibral compaction. Okay, the second method that we're going to talk about today is the deep compaction by explosion. So here we'll see how we can use and analyze the effect by the blast, by dynamite. And this technique is first developed in Netherlands or Holland, and explosions are used to compact the sand or the loose rock and the loess. And this soil has high porosity with distinctive soil skeleton. So it's very effective when you have some honeycomb structures that is very collapsible. Or the loose sandy structure that can be densified very easily using vibration. So basically install the pipe, PVC pipe into the ground, and at the tip of the pipe you install the dynamite or the explosive, and then you just explode it and then wait until it densify and then the settlement complete. So in the dry soil, when you apply this explosion, the explosion induces the shear stress, and this breaks the soil structure and reorient the particle, and finally you get different compression. So in the end of the explosion, you have this kind of a crater at the surface, ground surface. If this is where you detonate this dynamite, then the soil around this explosive will be densified. And when you apply this explosive or explosion in the saturated soil, because in the saturated soil, the water and the solids are incompressible. So this very large dynamic load can increase the pore pressure. So it will induce the excess pore pressure. So it can cause the liquefaction when the pore pressure over delta U over effective stress goes to 0. So then after the liquefaction, it deposits again in a denser form. So to speed up the settlement in the saturated soil, additional drains can be also installed, like a vertical drain or the paper wick. There are no acceptable theoretical design procedure for this explosion-induced compaction, but here are some useful guidelines. So first, the charge size, the explosion charge size, people use 1 to 12 kilogram of the TNT. And the depth of failure is, so you detonate this explosion at the depth about half to 3/4 depth. So if this H is the thickness of the layer that needs to be compacted, then you can install the explosion about the half depth or 3/4 depth. So between this range, it's okay. Yeah? So, but above the 1/4 depth to the bottom of the layer to be compacted is the recommendation. And the third is the number of coverage. So 1 to 5 explosion is typically used, but 2 to 3 usually used. And successive charges or successive detonation are separated by days or weeks because we need to allow the excess pore pressure to dissipate. So to have the complete settlement after one explosion, you wait about days or several days or 1 or 2 weeks, and then you explode it again. And because it's explosion, it generates a huge vibration. So care must be taken about the damage to the structure. So safe distance should be checked. So when the liquefaction occurs by this blast, say that this is the area that you detonate the explosives, then there's an important structure like hospital at the distance of R. So the R is the radial distance, and W is the weight of explosive. Then the first question will be how much pore pressure will be applied, will be generated. The second question is if this radial distance from the important structure is enough. Safe distance. And both this safe distance R and the pore pressure, excess pore pressure delta U, are related to the charge size W. So to determine this W and the R and the delta U, the people define this Hopkinson number NH, and NH is defined as W to the 1/3 over R. Here the W is the weight of explosive equivalent to kilogram of TNT, and the R is radial distance from the point of explosion. So when you apply this explosive, the explosion-induced compaction into grid pattern, say that the ground surface at the center of this grid pattern, here the R will be square root of S, half of S square plus half of S square plus half of H square. So H here will be the total thickness of the layer of compacted field. So say that your TNT or the explosive is here. So then how can we use this Hopkinson number? So Branson and Koch in 1983, they suggested this criteria. The Hopkinson number should be less than 0.09 to 0.15. So then the structure or the dead location of the R with the R distance R from the explosion will have a little or no liquefaction. So this criteria is typically used to determine the safe distance from the explosion. And for the sandy soil, we also want to find out what will be the delta U, excess pore pressure generated by this explosion. So delta U over effective stress can be calculated using this equation. And this equation is derived statistical approach. And you can see that when you know the NH, then you can calculate the delta U from this relation. Or if there's a delta U, the level of delta U that you have to achieve, then you can calculate the NH, and the NH is W as a function of W and R, so you can determine the R and the W, the weight of the explosive when you design it. So to induce the liquefaction, so delta U over sigma prime should be 1, and then the NH should be larger than 0.37 from this equation. For optimal liquefaction, delta U over sigma prime larger than 8 is required. And also, this Hopkinson number can be correlated with this crater depth over the thickness of the field. So then here, the delta H over H is function of like NH here, and this crater depth can be used to obtain or to correlate to the void ratio change, like E minus E naught. So this is similar to when we use the void ratio for settlement calculation. So if we assume or if we consider this delta H as a settlement, then also we can estimate the void ratio change in this compacted field.